Okay, so I'm going to share my screen. Guido, can you make the other guys?
Yeah, I take care of it. Don't worry.
Okay, full screen. Okay, so just before we start, as you can see now, I'm using a new version, 2.0.4, that will be released tomorrow. So by tomorrow, you will have the new STQO version on our website, a new OpenSys installer by the PUCP University, so from Professor Tarker's website, because we have these two new elements, so the absorbing boundary element and the contact element, and also all the files that I'm going to show you today. Okay, so by tomorrow you will have everything. So before we start, I will show you the contents of this webinar. I will mainly talk about the contact element. Okay, so we'll start with this one, and we have some examples. I will start with a very basic benchmark, a two-node contact. Then I will explain you how it works and how it is written in OpenSys, and then some other examples. So how we can use the same one for solid-to-solid contact, for contact in 2D and 3D with different orientations, and now you can do a soil pile interaction test, which is basically the same that we have done in the past webinar. But in the past webinar, we've been using the beam contact 3D model, and that model works fine, but it takes a lot to converge, so it has many convergence issues. And I will show you how much faster it can be with this new element. Then I will give you just a brief presentation about the new absorbing element. Okay, I will give you some examples so that you can run them. You can start looking at them and at documentation. I will not go into the details because this one will be the topic of the next webinar. Okay, so in the next webinar, I will go into the details of the theory, the implementation. Okay, but at least you already have all the files so that you can start playing with them. And finally, I will use the contact, everything that I explained in the contact, I will apply them into a soil foundation structure interaction test. Okay, so here you have the soil model, the structure, and then you have the piles and also a slab foundation and all the contacts. So basically all the concepts that I'm going to explain in this simple example will be gathered into one example here. And the idea would be in the next webinar to take this example, extend the soil model, and apply absorbing boundary condition so that we have everything in one single file. Okay, so let's start with the contact, and I will start with this model here, which is very basic model. So we can start by going into the contact folder, T01 two-node contact. Okay, this one is very simple. You don't see any geometry because you actually have just two nodes. Okay, two nodes that can be created with the vertex command. Okay, these two nodes are overlapping. Okay, then I create an interaction between them. N1, so the first node will be the master node, and node 2 will be the slave node. Okay, the interaction is a simple node-to-node link. And then it is very easy. Actually, one node is completely fixed, and the other node is free just in the X direction and also in the Y direction in the first stage. So I apply a vertical precompression in a first stage, and then in a second stage, I apply an imposed displacement in shear. Okay, why? Then I'm going to show you a little bit the theory about this one. But before we start, you have to think about that this element is actually a zero-length element. Okay, so let me show you. In fact, you can find it under model, zero-length elements, and you have the zero-length contact ASD implex. As you know, implex stands for implicit-explicit, and it is a new way of integrating the equations of the constitutive model. So it is a zero-length element. So before we start, we need to fix some concepts about the zero-length elements. because I've seen many questions also on the OpenSys Facebook group, because people are still confused on about how the zero length element works. Okay, so this is true for the contact elements, but also for any other zero length element. Let me do an annotation. So for any zero length element, okay, you have two nodes. Let's say N1 is the master node, so the first node of the element. N2 is the second node, okay? And then the zero length is actually an element that connects the two of them, okay? Now, how does the zero length element computes the deformation and the forces, okay? So the deformation, if this is U2 and U1, okay, so the displacement vector in global coordinates of the second node and of the first node, the strain of the zero element, which is not actually a strain, it is actually a displacement jump, okay, we can call it delta U, in global coordinate, is actually equal to U2 minus U1, okay? That's why it is really important, the order, okay? So what this element does is U2 minus U1. This one is the so-called generalized strain or displacement jump in global coordinate system. But then, before using this one into the constitutive equation, it is transformed into the local coordinate system, because any zero length element can optionally have a local orientation that by default is the global one, okay? Or the user can specify its own orientation. So finally, the delta displacement in local coordinate system is equal to transformation matrix transposed times du, okay? Where this transformation matrix contains the three orientation vectors, okay? So for example, you can have x3 or x1, whatever it is. Let's call it x1, x2, and x3, okay? So now, by default, any zero length elements has the local coordinate system, which is coincident with the global coordinate system. But the user can give its own local orientation. And it is really important, especially in contact, that the local direction here, the x1 in this case, points in the same direction of the contact direction. So why? Because, for example, if my global displacement jump is given by U2 minus U1, if this axis is aligned, then the sign of this quantity remains the same. But if you assign a different orientation, for example, in this direction, then this one, which can be, for example, if this node is displaced in this direction, it is actually a compression. But if you put it in the other direction, okay, it becomes subtraction. Pay attention. So you should really pay attention. And this is especially true for contact. So the common rule for contact is that N1, so the master node, is the node from the master surface. Okay, so master. This one, N2, is the node from the slave surface. Okay, so this one is a body, the master body, and this one is the solid body. And it is really important that the contact direction points from the master to the slave. Okay, otherwise, instead of having compenetration, you will see separation. Okay, so you have to keep this clear in mind, because otherwise you will see many mistakes. Okay, so delete everything and let's start. Now, in this case, I modeled, I think this one was 2D or 3D, let me see. Okay, we are in 2D. Okay, now in 2D, well, let me explain a little bit the element. You can choose whether it is a 2D model or a 3D model, but the element is the same, okay? Then you have two stiffness parameters. The Kn is the normal penalty stiffness, okay? So for to avoid compenetration, and the Kt is the tangential stiffness because this one is a friction contact. If you don't want to model friction, okay, you just want to model hard contact in unilateral direction, you can either put this one to 0, or you can put actually 0.0 mu to 0. What is mu? Mu is the coefficient of traction, the friction coefficient, which is actually the tangent of the friction angle. Okay. Why? Because this one uses the more Coulomb friction model. So let me do an annotation. If this one is sigma n, and this one is sigma t or tau, okay. The friction model, the more Coulomb friction model is something like this, okay, where the slope here is the tangent of the friction angle, so nu, and the resisting force here, so in this case you are in stick condition. If you are outside, you are in slip condition, so you move over the yield surface. And any point here, for example, the maximum shear force that separates the stick condition from the slip condition is given by minus sigma n times mu. Okay, minus because only if you are in compression. Okay, if you are in tension, of course, you don't have any friction force. Okay, so for example, if you put mu to 0, this surface actually is flat. Okay, so you don't have any, the shear force will always be 0. And the same if you put kT to 0. Okay. Okay, so let me little drawings. And finally, you have some other option. So implex is optional. By default, you can see it here. By default, the integration of the constitutive model is done in the implicit, so the standard backward Euler integration scheme, which makes the model nonlinear. If you use the implex, this one is pretty similar to the one that we already described in the damaged TC 3D model. Basically, the integration of the constitutive equation is made first explicit during the Newton iterations. And then when we do a commit of the internal variables, we do an implicit correction. That's why it's called implex. It's a mixed implicit-explicit method. The same rules that I've explained for the damaged TC model apply here. So if you use the implex, the model will converge much better. It will be much faster, but the time step should be smaller. And I will show you in some examples. Then you have this other option, which is available in also other zero-length elements, which is the distributed option. Now, this one is not inside OpenSys. It's an automation that we have in STKO. So basically, when you want to create a zero-length, which is not a node-to-node spring, but is spread over a surface or over an edge, you can click on distributed, and basically STKO will do a nodal lumping of these quantities, okay, using the tributary area of every node. Okay, so let me do another drawing here, just to explain you why. Okay, so if you want to create a physical node-to-node contact, you don't care about this one. But if you want to create a contact between one edge and another, okay, and then these two edges will be meshed, for example, in 3 parts like this, STKO will create 3 springs, okay, 3 contact springs. But instead of giving them all the same Kn and Kt, Kn and Kt will be scaled by the tributary area. So for example, this node will have, let's say, 0.5. This node here will have 1, and this node here will have 0.5. Okay, so these coefficients will be scaled by the tributary area. In this way, you can use this node-to-node spring to model a distributed contact condition. Okay. And finally, there are 2 other options. Okay, how you can define the orientation type. What is this one? Now, by default, well, it is all described here, but you have 3 options: from local axis, from element, or from link direction. Now, from local axis is the default, because this is the same behavior for every interaction in STKO. Okay, so an interaction has a local axis that by default coincides with the global coordinate system. But if you want, you can assign a custom local axis. Okay, then if the orientation type is the default one, so the from local axis, then this element will have the exact same coordinate system given by the local axis that you assign. And this is fine almost every time, okay? But sometimes you may need to, for example, imagine you want to, let me do another drawing. Imagine you want to create a contact between a body that is curved like this one. And I will show you an example of this. Okay, so you have many links put, for example, in the radial direction. You cannot use just one local axis because otherwise all of them will have a local axis which is aligned with this one, okay? Well, in this case, you want a contact direction that follows the master to the slave surface, okay? Now, if you want to achieve this one, we have this other option here, which is from element. Now, from element, basically you don't need to assign a local axis because the contact element will take the contact direction from the normal direction of the surface, okay? So you don't need to take care about the local axis by yourself. And finally, there is a third option, which is from link direction. And this one is only useful when you model pile to soil contact and when the pile is a beam, okay? So you have a physical distance between the center of the beam and the edge of the hole, okay? And when you have a distance between master and slave, okay, I can compute the distance between them. So I can compute the direction vector between them because the two nodes are not collapsed. Okay, so in that case, you can choose from link direction. Okay, now we can start with the default one, which is from local axis. And rigid gap is also useful when you use this one. So when you use from link direction and you have a physical distance between the master and the node, by default, that distance will be a gap. So the node will not be in contact unless the whole gap is, the node proceeds through all the gaps and touches the surface, okay? That is the standard behavior. But if your gap is not actually a real gap, it's just, for example, the gap given by the cross-section extrusion, okay? You can take it as rigid gap. In this case, we can simulate the beam contact element that was originally in OpenSys, okay? And I will show you an example also for this one.
Massimo, why do you need the master node to have rotational degrees of freedom?
In this case, you need the master node to have rotational degrees of freedom because when you click on rigid gap, what I do is this one. Let me do a drawing.
So it will behave like rigid link.
Exactly. So
Okay,
imagine you have a here and you have the solid body here, okay? This one is the beam center line, but actually you have a cross section which is like this one, okay? So for every node here, this one will be the master node. This one will be the slave node, okay? Now, by default, there is a gap here. And if you do not click on this option, the node can move up to here without generating contact forces, and only when it consumes all the gap, it will generate contact forces. But if you click on rigid gap, what I do inside STKO is to create an auxiliary node here. I create a contact between these two nodes, and this distance here is replaced by a rigid link. Now, to have a rigid link, the master node should have rotational degrees of freedom, okay? Otherwise, the rigid link, for example, this one cannot go up due to a rotation of this node if this one does not have any rotational dots, okay?
Okay, thanks.
Anyway, here you have all the description, okay? But in any case, I will show an example for each one of these options. Now, let's start from the very basic UA. Yes, you have a question?
Yeah, so like the problem you just mentioned about a beam and a solid, will it affect like whether the solid element is like 3 degrees of freedom or 4 degrees of freedom? Like it will automatically.
Yes, this is the nice thing of this new element. I forgot to talk about this one. The main issue that we have in OpenSys, and that you also had with the beam contact element, is that these contact elements work with 3 DOFs for each node, okay? And both nodes should have the same DOFs, okay? Now, in this case, this is not a problem because we implemented, actually, Dennis made the initial implementation of this element, then we proceeded together. But basically, this element can support in 2D can support 2 or 3 DOFs. So you can have just displacement or displacement pressure or displacement rotation. And in 3D, it supports 3, 4, or 6 DOFs. Okay. And the nice thing is that the 2 nodes does not necessarily need to have the same DOF set. Okay. So you can connect a 6 DOF node, for example, a beam, with a 3 DOF node of a standard brick element, or with a 4 DOF node with a UP element. Okay. So you don't have to care about that. It supports any kind of DOF set from master to slave. Okay. And another interesting thing is that the standard contact elements in OpenSys cannot be oriented. Actually, they can be oriented only in the global direction, X, Y, or Z. In our case, the contact element can have any direction. Okay, so it's much more user-friendly. Yeah, we have another question by Hernan Alfredo.
Hello to everybody. Thank you for this nice presentation. I've been following this Stick.io for approximately 4 months, and I find it very, very helpful for solving research problems and to have more opportunity to use all the capabilities of OpenSys. I've been using some contact elements. I've been checking also your webinars, and I have a question regarding if this element could be used to contact a linear beam element with a shell element.
Exactly. This is actually in the last example, I mix beams, shell for slabs and solids. It can connect anything. Okay. So don't worry. It can connect a solid to a solid to a beam, a solid to a shell to a beam. Okay. So there is no restriction. Okay.
And what's the main difference with the already existing zero length contact ST, the one that it's already available in Stick.io?
There are other, for example, I think you are referring to, let me switch this off. Let me see what contact element you are referring to.
With the implex contact.
Oh, no,
Zero length.
Yeah, no, it is the same actually. The point is that when we wrote the implex contact was already there. Okay. Now we had to change the name. Okay, for some internal reason. So we just changed the name. And in this Python here, I just added few automations like the orientation type, the rigid gap, the distributed option. But behind the scenes in the OpenSys code, the element is the same. Okay. It's just an SDK automation. So for example, the contact element is the same, except from the fact that I changed the name here.
Yeah.
For example, if you want to create a beam to solid contact, I do not create a new element. I just, as I told you before, I have 2 nodes. The user has 2 nodes. Okay. It creates an interaction like this. Then what I do inside is that if you use a rigid gap, I automatically create a new node here. I create a zero length element here, and I connect them with a rigid link. So you think that this one is a new element, but actually behind the scene is a combination of 2 components that are already in OpenSys, which is the contact element and the rigid link. Okay. So it's just another. Okay. Okay, so let's start with this first basic element so that you can understand how it works. Here I will just show you the more Coulomb yield surface of this one. So basic definitions, I'm 2D. The penalty stiffness in contact direction is very high because I don't want any compenetration. And then I assign a finite shear stiffness just because it's easier to visualize a graph this way. So I have 100 as KT, a 0.5 of the frictional coefficient. So the slope of the more Coulomb yield surface. Okay. Now in 2D, the contact direction is given by the local y-axis, while in 3D, it is given by the local z-axis. Okay. Now in this case, we are in 2D, so this one is the contact direction. And it is really important. That's why I use the first node as the slave, as the master, the second node as the slave, and then I apply a vertical force, okay, which points downward, okay? And this is fine because my contact direction points upward, so it is a compression actually. Okay, so I have my my interaction here, the contact element. The contact element is assigned to the interaction. You don't need any physical property, just the element property. Then the boundary conditions. I have a fixity, a complete fixity on the node 1, so on the master node. The master node is completely fixed. The slave node, so the node coming from above, in the first stage is fixed in the x direction because I just want to apply a vertical load. I need to fix it in the x direction because of course there is no element here. This is just a benchmark. I have no element here that restrains this node from moving in the x direction, okay? So I have a fixity for the first stage. Then I apply a vertical load onto the slave node, okay, a -10. And then I have an imposed displacement always on the slave node in the x direction of 1. Okay. Now, how do I apply everything into my analysis steps? So the first thing, you apply the boundary conditions. So the complete fixity at the base node and the fixity in the x direction at the top node. Okay. Then I create two monitors, one to monitor the normal force versus time. I just want to make sure that the normal force goes from 0 to 10 and then remains constant. And then I have a second monitor to monitor the shear versus shear displacement. Okay. Then I apply the vertical load here with a linear time series. And here I have the vertical load. And then I do my first stage analysis, okay? Where basically I apply the compression. Once I have the compression, with the friction coefficient, I have a friction force, okay? I have a friction resistance. So before I start the second stage, I have to remove the fixity in the x direction so that I can move actually the top node in the x direction. So I use a remove SP constraint and I remove the fixity in the x direction. I apply the shear load, which is in this case is actually an imposed displacement, okay? And since it is an imposed displacement, I can do a load control analysis, right? Okay, so let's do an analysis here and let's see what happens. In this case, it is a sequential analysis. So run. Okay, here I use a lot of time steps, but it is not necessary. Okay, so oops, here it is. Okay, so here I have two monitors. The first one is the normal. So as you can see, it goes from, well, this one is the time step ID. In the first steps, it goes from 0 to 10, which is my imposed vertical load. And then the vertical load remains constant for all the other 1000 steps. And instead, the second monitor is the tangential response. It's up to 5, and it makes sense. Why? Because I have a vertical compression of 10, okay? And the friction coefficient is 0.5. So if you remember, the friction, the stick force is actually equal to minus the compressive force times the friction coefficient. So 10 times minus 5, okay? And of course, this point that you see here, well, the point at which you have the change in slope is actually depends on this one divided by KT, okay? So this one is a simple benchmark to understand how it works. Now, for example, if I double the vertical load, you will see that I will have 10 here, okay? So let's just do it for a test. Let's put minus 20. And the shear resistance should increase. So normal direction, I have a 20 as compression, and then I go in tangential response, and my shear strength is 10 now, okay? So this is coherent with the Moore-Coulomb theory. Perfect. So this one is the very basic benchmark. Let me go back to the initial -10 so that I send you the original file. So you can play with this one to understand how the parameters work. Okay, so this one can be used as a tester to understand how your contact properties behave. Okay, now let's go to a second example. This one is called solid to solid contact. Now in this case, I have just two bodies, as you can see here, a bottom body and a top body. It is very simple, so I just want to show you that the concept of applying a distributed force, okay, a distributed contact, sorry. Now what I do here is that I have to be, it's similar to the example that I've done before, but before I had just two nodes, so I was assuming that the master body and the slave body were completely rigid. Okay, so if they are completely rigid, you can also just do not model them at all. Okay, but now in this case they have a finite stiffness, and the contact happens here in between. Okay, so if I switch off the faces, you will see that I have an interaction here in the middle for the contact. Then I also have an equal DOF top and bottom to avoid a rotation. Okay, I just want to apply a shear deformation. So that's why I have an equal DOF on top and on bottom. And for them, I use an equal DOF in the Z direction. Yeah. So this one means I don't want to see a rotation about the y-axis. Despite of this, the element is the same. Okay. So I just applied the distributed option here. Okay. Why? Well, for the same reason, because let me see, let's have a look at the mesh. Okay. Imagine the springs that coincides with this corner node should have a factor which is 1/4 of the factor of the element inside, and this one should be 1/2 of this one. Okay, if you don't do that, for example, you couldn't do that with the initial zero length element, the results will not be correct. Okay, but now here I want to show you the implex stuff. Okay, so let me start with the original contact. Okay, so I select this one and I apply the original contact element. This one, if you remember, is the zero length contact 3D. Okay. Now also here I implemented the distributed option, but the main problem with this one was the direction. It can only be oriented in either X, Y, or Z. Now in this example, it was fine because my normal contact direction is pointing in the global Z direction. Okay. But in a general setup, it is not possible. For example, imagine the pile inside the soil. The normal direction changes with the direction of the pile. Okay, so you cannot use the standard contact element, and also it takes a little bit to converge, and this one is much faster. So let's see what happens with the standard contact element. Of course, the properties are the same. So let's run this one. UP-UN, then let me go to tau. As you can see here, when it moves to the sleep condition, it takes a lot of iteration for this element to converge. Okay, so it is converging because the example is pretty simple, but look at how many iteration it takes. Okay, 30, sometimes 2, 6, but then it jumps to 30 because, well, contact has a lot of convergence issues. And then you will see the way we implemented it is much faster. Okay, so let's say now we are about at 1 minute and we are 50% of the analysis. Okay, the results is correct, is what we expect, but it is taking a lot. Okay, now let me just stop it. Let's say for half of the analysis, it took 1 minute. Stop. And let's change it to our contact element. Now I don't want to even use the implex method, just the standard implicit, which is still nonlinear, already converges much better than the standard element. Okay, so let's do this test, run analysis. let's see the tau. As you can see now, you have 7, 6 iterations. You don't have all those iterations, okay? And you can see it's much faster. Now we are at half of the analysis in 17 seconds. So much faster than the other, and it's pretty stable. As you can see, 7 iterations. It is not jumping from 2 to 35, which is kind of strange, okay? So at the same time, here is already finished. And now let's move to the implex instead. Well, in this case, you will not see a lot of difference because this example is very simple, but in many cases, also this contact element here, which is very stable, it does not converge in some complicated stages. But the implex method can almost guarantee almost every time a convergence. This is not completely true in contact, because in contact, it may happen that you don't, and if you're doing a static analysis, it may happen that at a certain point, you don't have an equilibrium point, okay? So even if the element is stepwise linear, but you don't have an equilibrium configuration, it cannot converge, of course. Now, if I go with the implex and I run the analysis, you see? Now I'm going to explain you what is this oscillation. Now you can see the number of iteration is much lower, okay? So the analysis will be much faster. But as I told you, you have to pay attention to the number of time steps and also to another thing that I will explain you in a while. So first of all, you don't have to worry too much about this oscillation, because as you can see, they are given by the fact that you have an explicit extrapolation of the internal variables, but then you have an implicit correction. So as you go further in the analysis, this error is minimized, okay? So it's not like a pure explicit analysis where this error grows, okay? If you reduce the time step, this one will reduce as well, but it will also reduce if you reduce the tangential stiffness, because in this case, I used a very high tangential stiffness, but it is not necessary to use such a high tangential stiffness. Let me show you. Because here, for example, you can choose, now here, if I remember correctly, I had an elastic isotropic medium of 30, so 3 to the power of 4. So I use, when you pick the contact stiffness, okay, here you ideally need an infinitely stiff value. That would not be possible, because otherwise your system would be ill-conditioned. So what I typically do is I take the stiffness of the material and I increase it by 2 or 3 order of magnitudes. Now in this case, 2 order of magnitudes. Then here I did the same with KT. But actually this is overkilling. This is not necessary, because the tangential stiffness should be physical, in the sense that friction is given by the asperity of the contact surface. And this asperity is made of a material, which is the same material of the two contact bodies. So you can assume that the tangential stiffness is actually equal to the shear modulus of the material divided by the thickness of multiplied by the thickness of the interface. So in this case, it is not necessary to make it this high. For example, if I keep it only 1 order of magnitude higher than the default shear modulus, you will see that those oscillations will be reduced a lot, while the solution is still the same. Okay, now as you can see, they are also almost minimized. If you want to further minimize them, you can also decrease the time step. Okay, but the nice thing of this one is that even if you have to decrease the time step, it guarantees convergence. Okay, so this is really important. And you will see it in more complicated problems. Okay, so this one is a second benchmark. Now let me go to, well, in this case, as I told you, this one is the same example that I showed you before, but instead of having only 2 nodes, here you have a full model with the 2 contact bodies which are deformable, okay? So in this case, you have learned what the distributed option can do, and also the difference between implex and implicit, okay? And so the performance boost that it can have. Now we have other two examples that actually show you how to use the other orientation types. Okay. So by default, also here, as you can see, I've used the standard from local axis. Now, when the contact configuration is a little bit more complex, using local axis is not affordable. So I will show you some other option that you have. Now, this one and this one are the same. So I will show you, well, let me show you the second one, the 2D one. Okay, now let's say you have to create a contact element between two bodies. Okay, now this one is the master body, the coarser one, and the finer one is the slave body. Okay. Now, first of all, in this kind of situation, when you have different meshes, you cannot create a node-to-node contact. Why? Well, because here I could create a node-to-node contact here as well, but I cannot create a node-to-node contact here in the middle because for this slave node, I don't have a corresponding master node. So using standard node-to-node contact.
Massimo.
Okay, really strange.
Yes.
Okay, that's fine. Well, Zoom went crazy for a second. Okay, so where did you lose me when I imported this file?
Yes, so we didn't see the file. So you were talking about two different files. We missed that.
Exactly. I was talking about, now I've just explained the solid to solid contact. Then we have these two files, T03 and T04, which is basically the same example in 2D, okay, this one, and the next one that I will show you in 3D, that basically explain you why you may need these options here, okay? Instead of using from local axis, you have from element, okay? And then later on, I will explain you the from link direction. Now imagine, as I told you, when you use the from local axis, it is fine as far as the contact direction is constant, okay? So if it is constant, like in the previous example, like a flat face against another flat face, you can use the local axis. But when you have a more complex contact configuration like this one, where basically the contact direction changes at every point, using the local axis is not feasible. And then you have also another problem. Imagine you have two different mesh discretization between the master, okay, which is typically coarser, and the slave, which is typically finer. You cannot create directly a node-to-node contact because here, for example, you have a node on the master and a node on the slave surface. But here, for example, for this slave node, you don't have a corresponding master node, okay? So in this case, we made an automation. Now, instead of creating the interaction, the contact interaction as a node-to-node contact, I added the opportunity to create a node-to-element link. When you use node-to-element link, the element, the master surface will create the element part, and the node will be on the slave. Okay, so when I say node-to-element, it means master element and the node is a slave. Okay. Now, if I do this and I select node-to-element interaction, I can select the first surface as master, the second edge, which is this one, as slave, and it will create this sort of interaction. So each slave node, okay, will be connected to the nearest element, okay, so the nearest surface. Now, this is not important because actually behind the scenes, this one is not connecting, it's not making the contact between this one and this surface, but actually with this edge. Why? Let me create an annotation here just to explain you and why I need to use a surface in 2D, but in 3D will be much easier. So basically, this one is the master triangle, okay? And let's say here I have the slave node. As you can see, I cannot create a node-to-node contact because I have a node here and a node here, but I don't have any node here. But when I choose this option, so node-to-element, what I do is that I take the nearest element, I project the node using the outward normal direction of the edge. I project the node here onto this element. I create an auxiliary node. This node will be connected to these other two nodes, okay, using the embedded condition. Okay, so basically this node will move exactly on this edge. without creating any additional stiffness on this edge, okay? It will just move according to the position. If it is on the middle, it will be a weighted average. So this displacement plus this displacement divided by 2 is, if it is here, it will be 2/3 of this one plus 1/3 of this one, and so on. So basically, the automation is that I take the master node, I take the slave node, I projected it onto the slave edge. I create an auxiliary node. The auxiliary node is embedded into the master edge, and then I create the contact between them. Okay. The nice thing about this is that since I have a super surface like this one, I can compute automatically the normal direction, which is this one for this triangle, which is this one for the other, and so on. That's why it is really important here to use the, where it is, the from element orientation type. And as you can see here, the from element orientation type can only be used when you use a node to element interaction. Okay, because of course I need an element to calculate the outward normal vector. Now, if you run this analysis here, it's just a simple analysis where I basically fix this one in both X and Y direction. I fix this border here only in the Y direction, and I apply a pressure here. And the output is this one. Let me go in contact, E03 okay. Now in this case, I made, as an extra example, I made a pure normal normal contact because I put mu to 0. Okay, so in this case, I also explain you how the friction coefficient work. If you look at the deformation here, you will see that even if they are not coinciding, okay, they will still be in contact, because in fact, if I try to see the nodes here, okay, and I click on this one, you will see that actually I have two nodes, okay, the one and the extra node that I created, okay. Okay, so let's go ahead. Oh, and now, as you can see now, I didn't use any friction coefficient, and you can see that during contact, this one slides very fast. Let me go here. Okay, you can see it is in contact and slides a lot, okay, because it has no friction. This is pure normal contact. Now, if I take this one and I increment the friction coefficient, like let's say something very high, 0.6, and I run the analysis again, let's see the difference.
Massimo, is there a particular reason why you use triangular elements?
No. I'm just using triangular or quadrilateral is the same. As you can see in the next example, which is the same one in 3D, I'm using xi lever. Is exactly the same. I just forgot to change the mesh type, but it makes no difference here. So if I reload now this one, okay, you will see that they stick much more. Okay, they do not only it does not only push it in the X direction, it's still, as you can see here, is trying to keep the contact surface at the same position due to the high contact friction. Okay, it's not sliding that much. It's almost stick. Okay, and that is the role of friction contact. Okay, so here you have learned the node to element interaction combined with the from element local axis. Okay, this is very convenient when you have edge to edge, or even easier when you have face-to-face contact. So if you go on T04 contact 3D orientation, you have the same problem, okay, but 3D. Okay, and now here it's even much easier, because when you define the contact interaction, which is still a node to element, the master surface is the surface from the coarse body here, and the slave surface is the surface from the other body. Okay, and also in this case, this is the output. Let me go here, P04. Okay, same as before, same result. Now in this case, it was the example with without friction. And as you can see, they are perfectly in contact, even if the mesh do not coincide. And this is very convenient. Okay, so a combination with the contact, combination of contact and embedded element can easily allow you to perform this kind of contact operation. Okay. Okay, so this is fine. And now let's move to the last example to show you what is instead the third option. The third option is from link direction combined with the rigid gap. Okay, so that option can be used to model the pile to soil when the pile is modeled with a beam. Now, if you remember, actually here you can find the T05, sorry, soil pile test, which is actually the same file I used in this previous webinar soil pile interaction. Okay, I think this is the last one I did in May. But in this case, I was using the contact 3D model. Okay, now let's see the differences between them. Now, if I go here and I grab the original file. Now, in this example, if you remember, I explained how to perform the staged analysis. So the first stage, I have all the soil with the hole here. Then I perform an excavation. So I remove this whole domain. Then I apply the pile, and then I do the pushover. Okay. Now, without going into the details of this kind of excavation analysis, because you can watch that webinar to understand the different steps that I have here. The concept here is that I was using the beam contact 3D. Then there is the contact 3D version, which is the Lagrange multiplier version, and there is the beam contact 3D-P, which is the penalty version. Now, what you had to do in that case was to define a contact material. Okay, with the contact material, define the shear friction stiffness and the friction coefficient. And then you define the contact 3D. Actually, you need two different kinds of contact. The first one is for the sides, and then you need the beam end contact, which is the contact for the bottom of the pipe. Okay, so there are two different elements. In each one of them, you have to specify the radius for the rigid gap. Okay, while in our case it is automatically computed. Now in this case, the gap was 0.5 meter, the radius. Then you have to specify the transformation, the coordinate transformation, and a few other stuff here. And same for the bottom. Okay. Then this one had a lot of numerical issues. So if the radius of the beam was 0.5, in the beam end contact, you have to make it slightly larger. So you have to add a small tolerance. And in the beam side contact, you have to put it a little bit smaller. I think we have a question. In this case, how do you select the value of G? Oh, now this is the same. Whenever you have to select the value of G, it's up to you. You have to understand what is the asperity of the surface. So the concept is that if two surfaces are ideally flat, you should not have any friction. Okay. So typically, it is you can take the G of the material divided by the size of the asperity, but it is really hard. There are many papers that explain how to get those values. I typically use something which is close to the shear modulus of the material. Okay, and G is not the only problem actually, because if you take the shear modulus of the material divided by the asperity size, it can be 0.5 centimeters, for example. It's fine, but you still have to calibrate the friction coefficient. Now, in this case, for example, the friction coefficient was, I don't remember, let me see. It was 0.15. That really depends on the friction angle. Probably should be, now in this case, I think it is slightly less than the friction angle of the material model, of the soil material. Okay, I think it should be slightly less. You mean a G close to the material of the pile? No, the soil, yeah, the soil, because it actually is the softest one is that one. Okay. Okay, so now if you remember, this one takes quite a lot to converge. And one thing that I wanted to show you is that I had to use in that webinar, I had to use the Newton with line search. Now let me just show you what happens if I use something different like the Krylov-Newton. I often use Krylov-Newton when I have softening problems, but I found that with this contact element, it doesn't work at all. So I try to run the analysis now. Now we have the first steps. This is the excavation step. And now in a while, it will start the pushover step. So when it will be in contact. Now here, it is starting the pushover. And as you can see, it is already taking a lot of time. Okay, the first iteration is done with 24. First step is done with 24 iterations. And let's see what happens next. When it takes so much, you can already tell that it is, as you can see, convergence problem. You see here, the residual is very high. And trust me, it will take forever for doing this. So since I had this problem with the original element, I found that the only solver that was able to solve it in a reasonable amount of time was the Newton with line search. Okay, which is this one. And this one is the one that I used for the webinar. It still takes a lot. I think it will take 30 iterations for each step. Let me see. And then I will show you the new element. This one is the gravity analysis, which is pretty simple. Now, in this case, for example, this one is a contact problem, which is much harder to solve with respect to the example that I've shown before. So now with the Newton, with line search, okay, you have 14, 12 iterations. Let's see the trend. I should be slightly higher. Okay, 19. So the average number of iterations should be around 20. Okay, sometimes even more, 30, but okay, it will take a little bit. Yes.
Is it because Krylov-Newton do not update each step, or because of something else?
Actually, it is really strange, and I will show you that even if the two elements give the same response, I will show you that our element, I talk about our element because you also implemented it, it works really well with Krylov, while with the Newton-less search is pretty similar to this one. But if you use Krylov, it converges incredibly fast. Now, the problem is a mathematical problem, actually. So I didn't have time to look at it. But with the Krylov-Newton, where this one does not converge, our element goes really well. And I'm not talking about the implex, also the standard implicit method. Okay, so now without wasting time with this one, I will go with this test, okay, which is the same. I simply converted it to our own contact element. Okay, so how did I do this conversion? So the interaction is the same. In this case, for a pile, which is a beam embedded into a soil, it should be a node-to-node link. Okay, a node-to-node link where basically the master and the slave have a finite distance. If this is true, I can use these options. So I go here, and I have contact at site, for example. The coefficients are the same of the other material model. You can choose now from link direction, okay? Because from link direction can be chosen when you have a finite distance between them, so I can compute the direction between them, okay? And then, of course, I don't want this initial distance to be a gap, but I want to fill it with a rigid link, okay? Now, as you can see here, I don't have to introduce the radius of my beam because I already take it from the norm of the slave node minus the master node, okay? So there is no need to specify the radius of the beam. So this is fine for this. And instead for the bottom, you have to specify a local axis because for the bottom, okay, I cannot take the link direction because if I switch this off, you can see that the contact at the bottom, which is this one, select. If I take the link direction, it will not be the correct contact direction because the contact direction here should point to upwards, okay? So towards the plus Z direction. So here you need a local axis. So for the bottom, you select from local axis, because by the way, the bottom surface is flat, so you just need one local axis. And it is really important that you choose it as a -c. Why? Because the master is the, as I told you before at the beginning, the master is the pile, so it is above the soil. So the contact direction should point from the master to the slave. So -c. Okay. Okay. So that being said, this is extremely easy. You just change them. You don't have to do anything else. And another thing that was really annoying about the previous example is that, let me do a simple annotation here. If you remember in that webinar, but you can look it from the previous file if you don't remember, when you use the beam end contact and the beam contact 3D element, you have to take care about the discretization of the pile and the soil. So if this is the pile, the soil element should be somewhere inside these bounds, okay? The soil element, the soil node cannot be here at the same direction, because if it is here, for some numerical error, for example, it may happen that it is slightly higher, it doesn't find any contact because this one is in contact with this element. But if this node goes slightly above the top node, it will compenetrate. Okay, and it was really annoying because when you define the mesh size, you have to take care that each node of the soil coincides more or less, not in the middle, but in between these two bounds. Okay, and it was really hard to achieve this kind of mesh. Now, in our case, this is not the case. Okay, we can have, actually, we do need to have the same mesh, which is perfectly fine. In fact, if I go in a front view and I switch this off, you can see that each contact is aligned. Okay, the node of the soil is aligned with the node of the beam, so it's much easier. Okay, so that is the only difference. And remember the local axis here. Oh, something that we have fixed in this new version is that the local axis now has a fixed size in graphics. Okay, this was really annoying for people using a lot of local axis. Okay, now it is fixed in the screen space dimension. Nothing to do with the theory, but it's just a graphical stuff. Okay, now if I run this analysis and if I run it with the Krylov, which was not running at all with the previous contact element, where is it? Krylov, which is much more performant because it computes the stiffness matrix only at the first step in this case. We run this analysis, you will see that it takes, I think, the average of 4 iterations or 6. Let's see. Yeah, 4 iterations more or less, 4 or 5. That is the trend. Okay, so basically this analysis finishes in 2 minutes, while the previous one needed something like 14 or 15 minutes. It's much more stable, as you can see. Now let's wait just 1 minute so I can show you the result of this one, and then we move to the last example. In the meantime, if you have any question about the node, yeah, you wait. Yes.
I just wondering because in the ethical forum, I found that lots of discussion about because right now you are using the body force to generate the weight of soil, right? But if in the previous contact element, you will show some convergence error at the stage of cell weight, because if we apply the gravity law, then you will show some convergence error at the very beginning. But with the current contact element, will it also be an issue, or you will be fine? Yeah.
As I told you, with the previous element, for some reason it was showing convergence error since from the very beginning using the Krylov Newton method. Okay, I usually, yeah.
I mean, it's like when we define the weight of the soil, we can like you applying a gravity force, right? Like minus 9.81, and doing the transient analysis.
But are you talking about the settings of the transient analysis or what? Now here in my case, I'm doing a static analysis here.
Yeah. I mean, because in the previous like contact element, like the old version 1, when we use transient analysis, and using the contact element, it will show the convergence error. Either I use the Kyle Newton or like Newton with line research. And if we also look at the post-processing part, we can see that your zero length element will like goes crazy.
No, I mean you're saying the jumps that you see in the implex method. I don't get what you're saying about
Okay.
the previous example.
Oh, no, I mean now the way you add the soil weight is by using the body force, right? The body force.
No,
In the condition when you set up the weight of the soil.
I cannot hear you. Can you repeat? Sorry, you wait.
Yeah. So I mean the way you model the weight of the soil is by adding the load force in your conditions step.
No, I really cannot hear you. If there is something wrong with this microphone, I can hear you really bad. Can you write it on the chat, please? Are you using the chat, you wait? Okay. Can we use this contact element even when we're modeling the gravity force by using minus in transcendental adding volume forces? Actually, yeah, you can, but that's why I do not understand why you're making a difference between gravity forces by using minus 9.81. I mean, you don't want to apply the forces, but you hope that just with the mass you can have the volume force. Oh no, you're talking about the self weight of the solid elements which is applied all at once. You're talking about that one. Oh, okay. Yeah, it is fine, but probably you will have some problems also there because it will not go crazy as the previous contact element. But if you expect the gravity load to take a lot of iteration to converge and you want to reduce the time step, it's better to use the edge force or the volume force that we have in STKO rather than the volume force of the element, because in any case, whenever you do a nonlinear analysis, having the load applied all at once is not good, okay? Especially for contact. Now, in our case, it will converge, but as I told you, the implex method needs some time steps to avoid those oscillations, okay? So in my opinion, I always prefer to use an incremental volume force rather than the volume force of the element, okay? Actually, in STKO, it's super easy to do it, okay? Because you don't have to worry about writing all the node forces. So if you use STKO, it's much easier to use the volume force command instead of the body forces of the element, okay? Okay, so as I told you, this one, couple of minutes. Oh, we still have something in the chat, okay. Couple of minutes for the entire analysis and an average of 4 iterations. So it is much faster than the other. Okay, so let's go to the results just to show you what's going on. So post processing, open, and we are here, solve by test. Okay, if you want to look at what's going on inside, we can hide these solid elements. Oh, we have another question. For any analysis, while we are testing norm spin command, is the tolerance 10 to the -4 sufficient to get quite accurate result? It depends, because if you use norm disp inc, it means that this tolerance is absolute. So for example, if you're using meters, then 1 to the -4 is 0.1 millimeter. Now it's up to you to understand if it is acceptable or not. It depends on what kind of structure you're modeling, but if you use millimeters, it can be acceptable. Okay, so this one is a relative tolerance. For example, in my case, I'm using -6 or -7, probably, let me see. Yeah, -6, because I'm modeling it in meters, and I want it to be at least the tolerance of 1 micrometer, okay? Because for me, 1 millimeter in displacement is a lot. So if I use 1 - 3, I can commit an error of 1 millimeter, which is too much for me, okay? So I want to decrease it to 1,000 times. So keep in mind, this one is absolute. It really depends on the unit system you're using. So yeah, if you're modeling in millimeters, it should be fine. In meters, I don't think so, because 0.1 millimeters in structural analysis is a lot, okay? It is a lot to be considered negligible. Okay, so let's go ahead. Oh, I was talking about post-processing. We can hide this one to see what's going on inside. Hide. We go in the front view. And basically, as you can see, what we have done, yeah, let's go back to the origin analysis. At the beginning, for those who has not followed the previous webinar on soil modeling, at the beginning, the soil was complete, okay, there was not the hole, just the gravity analysis of the soil. Then in the second stage, I performed an excavation, okay? So this excavation creates extra displacements here. And then in the next stage, I bring the displacement to 0, keeping the internal stresses. This one is called initial state analysis. And I apply the structure. In this case, it is the pile, okay? Then we perform the settlement of the pile, so vertical analysis of the pile. And then we start pushing it in the X direction, okay? So you can see here is what Yue was saying. Here, to perform this settlement analysis, I used an incremental gravity load. While if you apply the self-weight directly in the element, you cannot do it incrementally like this, okay? So that's why I prefer always to perform incremental analysis, also for the gravity analysis. If you're wondering what are all these edges here, they are the contact springs, okay? If you don't want to see them, you can get rid of them in the usual way. For example, you can create a selection set with everything but the interaction, and you put that region inside the recorder command, okay? Like here. So if you do that, you can get rid of them, but it's not a problem for me. I can visualize them, okay? Okay, so in this case, you have learned all the 3 different ways you can use the same contact element. So as a node-to-node contact with local axis, as a distributed contact using the element normal contact direction, or using as a pile, as a beam to solid contact using the rigid gap, okay? So these are 3 different options, all with the same element. Now, we are running out of time, so I just want to explain you what we have, because this is not the only element that we added in OpenSys in this new version. The other major difference will be another element here, which is the absorbing element. And also here, we've already done a webinar on absorbing boundary condition. Dennis, you have worked a lot on this, also Yue. And if you remember, there were a lot of steps you had to do to perform an absorbing boundary condition analysis, okay? Now, in this case, we have implemented a new element. Okay, this one will be the documentation that you will be able to see now in the new OpenSys documentation. The element is called ASD, absorbing boundary, 2D or 3D. Okay, the 2D is a 4-node element. The 3D is an hexahedron. The parameters are really simple: the shear modulus of the material, the Poisson ratio, the mass density, and the thickness in 2D. And then a few other stuff here. All the documentation is given here, but the theory is this one. So you can see exactly what I already explained in the previous webinar on absorbing boundaries. But in that webinar, we had to do everything manually. So we had to create a soil domain on one side. We had to create 4-node elements for the free field. Then we had to apply equal dot condition to make this element behave as a free field. Then we had to add dashpots to simulate the Leismer-Kuhlemeyer boundary condition. But these dashpots are only used to absorb outgoing waves. So imagine you have a wave that starts at the bottom, hits the surface, then you have some imperfection. So these waves goes back in this direction and they will be absorbed here. But there was an extra component, which is T here, which was not possible to include in the with the tools that were already in OpenSys. So the formulation that we explained in our previous webinar was fine, but not completely correct. There was a missing component, and this one is the missing component. And this is the reason why we decided to implement a new element that does everything in a single computation. So this extra component is the boundary traction that are transferred from the free field to the side of the soil domain. And this is required to impose the free field condition on the soil domain. We have a question on the chat. I just want to clarify the previous question. Suppose I have a soil domain of 100 meters long and 50 meters depth with a structure on the surface of soil domain. Is sufficient for introducing gravity stress precisely? Yeah, I told you, I don't think so, but it's not the problem of the size of the model. Okay, the problem is the unit you are using. For example, if your structure can be 100 meters or 1 meter, that is not the problem. The problem is that if you are using meters as a unit system, okay, then 1 to the minus 4 means that you are accepting an error of 0.1 millimeters. Now it's up to you to understand if it is enough or not. For you, 0.1 millimeter is negligible or not? Well, if you're doing structural analysis, 0.1 millimeters is a lot of displacement for concrete or steel or even soil. Okay, so the point is this number times your unit system, so you're using meter, 1 to the minus 4, 1 meter, is small enough to be considered 0? In my opinion, if you're using meters, this one is probably too high. Okay, so I typically when I do meters, I use 1 to the minus 6, and I can accept this one if you're modeling in millimeters. Okay, so as I told you, it's not important how large your model is. It is important the unit system you're using. Okay, is it clear? And I think Professor Scott talked about this one in one of his posts. He was talking about the difference between an absolute tolerance and a relative tolerance and all the effects it has in OpenSys. I think he made a post on this. Okay, so going back to this example, the problem that we had is that in the previous version of OpenSys, we didn't have any way of imposing this condition here, so we decided to create a new element. Now, this new element is actually a 4-node element in 2D or an hexahedron in 3D, and it does everything inside. So these first 2 nodes are used to compute the free field response. Then the distance between node 1 and 2 and node 4 and 3 are used to create the dashpots, but also to transfer the stresses of the free field on the soil domain. And this one makes the solution correct. Okay. Now here there is a little bit of explanation of how to assign the boundary codes. So you have to specify if it is a bottom layer, a left layer, right layer, or bottom left, bottom right. And in 3D is a little bit more complicated because you have many more combinations. You can have left front, left right, front back, left front, bottom, and then you have the corners, which are a combination of 3. Now we are working on making this automation much easier, but then here you have all the explanations, what is the effect of the mesh distortion, and all this stuff, some benchmarks, okay, directly in Tcl without using STKO. And here I shared some examples to understand how they work, okay? Now we'll not go into details, okay? You can look at each one of them. And in the next webinar, I will describe very clearly the theory about this element. And I will do a step-to-step tutorial on how to apply this kind of condition. Now, just to explain you these models, I will show you all of them just briefly.
Massimo, one question. So can you describe, like, can you pick the material inside the boundary condition, or is it elastic material? For example,
no, it is an elastic material, but you have the opportunity to update G with the update parameters. Okay, if you are referring to. Okay. And
I mean, the theory is like, so it should replicate the tractions, so that the waves are like cancelled out because of the deconstructive interference. If the materials are not same, then the waves might not be exactly the same.
Yes,
right? So,
yeah, this is true. The point is that I had the option to use either a material or a linear elastic behavior there. The problem is that the whole theory about the absorbing boundary is based on elastic wave equation. Okay, so I don't think I think I could have had a lot of troubles using a nonlinear material. Okay, instead I prefer to do something different. I use a linear material inside. Okay, because those equations are based on elastic wave propagation. Yeah. But then I let the user update G. Okay. So what we can do, for example, is to find, then you have another problem. How do you define G using a certain material? So for example, I think with materials like PDMY, you can ask for the backbone in the result and you can get somehow the G. But also in this case, it's not so easy. So we need to think about it, okay? So that is a topic that also in other softwares have not dealt with, okay? So it is a really complicated topic.
Yeah, okay. Thanks, Massimo.
We have another question here, Gabriele. Have you quantified how much are the differences in the results between the two different methods? Okay, now I need to understand what are the two different methods. You are referring to the tolerance, the previous question, or to something different, Gabriele? If you want, you can use the microphone too.
Yes. The first is the old, let's say, FLUC-based method. Yeah. And the second is this new element.
But actually the theory is the same because FLUC is using the same theory. Okay. What I was saying is that before we were trying to simulate what FLUC was doing, okay, and also other softwares. The problem is that we were missing one component. So the transfer of the traction from the free field to the soil, which is this one.
Yeah, no, this is clear, but no, I'm just wondering if
there is a quite important difference. The main difference, actually, we don't have time now, but actually I can try to do something. I can try to switch this off so we can obtain the same results we had in the previous version. And then I will show you what happens. Okay, so let's have a quick test. I think we need a couple of minutes to do this. But let me just first show you the models. Okay, so if you go here, you have a test 2D. It's a very simple test. You can see the geometry and the properties. As you can see here, you just need to define your solid. Then you define some layers here at the sides. And then you define 4 elements. Okay, actually 3 elements, another 2, because you have bottom, left, right, bottom, left, bottom, right. You assign them. In each one of them, you can use a single material which contains the G, V, and ρ of the same material which is inside. And here you just need to define the type of boundary. Now, don't worry about this because I'm working on an automation that can automatically detect the sides, okay? So you will not, by the next webinar, you will not need to define all of them. You can just define one and we can find the proper boundary code. Okay, if you run this one, and you will be able also to see the monitor in real time, this is the output that you have. Absorbing 2D. And now we will do a simple modification to see what happens if I switch off one of those components. Now here at the base, I've applied a Ricker wavelet. Or you also have to pay attention to what is the input that you assign here at the base. The input should be a velocity field, okay? Now in my case, I wanted to apply a Ricker wavelet whose peak was exactly G, okay? So I took the derivative of the Ricker wavelet, in this case it is normalized, sorry, the integral of the Ricker wavelet, and then I multiplied the integral by G, okay? So this velocity field will actually apply the same acceleration. Now in previous webinars, the user had to manually take the velocity and multiply it by the rho times the shear wave velocity. Now in this case, it's all done inside the element, okay? You just need to choose the time series, and here it is all explained. The time series used as velocity, okay? It will be automatically multiplied by the Vs wave velocity, the thickness, the rho, and 2 to compensate that half of the acceleration that is absorbed by the dashpots, okay? But I will go into the details in the next webinar. In the meantime, you can have a look at it, you can look at the documentation, you can understand how it works. Now, as you can see here, the maximum acceleration that I'm expecting is 9.806. Okay, so let's have a look. I don't want to see any deformation. Okay, so 0, I just want to see the acceleration. Oh, and the nice thing is that this element also does a lot of other things automatically. If you remember in the previous webinar, I told you that you first have to apply fixity condition, then you have to remove them, you have to replace them with the equivalent reaction forces, then you apply the absorbing boundaries. In this case, this element is doing everything automatic, okay? So in a first stage, and you will see here, in a first stage, it acts like a fixity condition. Then you update the parameter stage from 0 to 1, and it becomes an absorbing boundary. So it is, as you can see here, I don't have any boundary condition, okay? This one does everything. So it does the static condition during the gravity analysis, and it is transformed into an absorbing condition during the dynamic analysis, okay? So it is extremely much easier. As you can see here, you don't have to do all the steps that we have done in the previous webinar. Okay, and if you run this analysis, you run the simulation, you will see the wave starting. Actually, I don't want to see the magnitude because I have acceleration in both x and y. I just want to see x. Okay. So here you can see the Ricker wavelet going from, yes, this one, 0 to 9.1. It hits the surface and goes back. Okay, and it is absorbed. If you look at the, let me remove also this one. The minus is minus 4.5. Okay, now it is fine. Okay, so you see here the Ricker wavelet deformation, positive, minus, minus. This one is actually G. This one is half of G, more or less. It hits the surface, it becomes the double, okay, because on the free surface you have the double of the acceleration, goes back and it is perfectly absorbed. As you can see, even if it is really meshed here, the solution is the free field one. So this one is the absorbing boundary, but inside you have the same correct solution. Now we will see what happens if you, or actually what happened before. Oh, there is another. Can you clarify that in order to produce acceleration history of 0.001 meter per second square as an input at the absorbing boundary, we have to integrate it to obtain velocity history, and then we can apply it, right? Exactly. So the idea here was to have an acceleration like this one, okay? As you can see, the peak is 9.81, so exactly G. So what I did is to, well, I went in MATLAB, okay, I plotted the Ricker wavelet. I took the integral of that. If you are in MATLAB, you can use the Cum-Traps function or whatever you prefer. You took the integral and you obtained the velocity. Now this one here, the values that I applied here are the integral of a normalized Ricker wavelet, whose peak is 1, okay? That's why I use a factor down here, such that the peak will be G, okay? So you take the acceleration and you convert it to a velocity, okay? You can use the multiplication factor here, or you can use 1 here and put here the derivative of a real Ricker wavelet. It's not important. You take an accelerogram and you convert it to a velocigram here. Then when you apply, then you can take this time series and apply it directly to the boundary condition, okay? Because then the boundary condition will take care of doing all the conversion, okay? Because then from a velocity you have to convert it to a stress field, okay, using the VP and the rho and the thickness if it is a 2D problem. And there is also this topic here. It should also be multiplied by 2, because half of the, and this is also explained in the FLAC manual, half of the velocity that you apply at the base will be absorbed by the absorbing boundary that are at the base, and only half will go inside, okay? So this element automatically scale the velocity field by 2, okay? So it is completely automatic. You want an acceleration, you obtain the velocity for that, you put it here, and you obtain the acceleration that you wanted here at the inside, okay? So as you can see here, the solution is correct here, and you also have the monitor. Here I created 2 monitors, okay? Let me just use the Y. 2 monitors. 1 to monitor what's going on in the input, which is almost 10, 9.8. Okay, this is what happens at the input. Then the wave travels and hits the surface, actually hits the surface here in the middle, goes back, and here is where the waves goes back to the bottom, and it is absorbed. As you can see, you don't have any reflection here, okay? And all this is also explained in the theory manual down here. In this example, I also put another recorder on the top so that you can see the blue one is the recorder at the base. So you see the acceleration which is entering the soil, okay, goes here, hits the surface. When it hits the surface, it is a free surface, so you have double the acceleration because I don't have any really damping here. And then the acceleration goes back to the bottom and it is absorbed. So perfect solution that you would obtain, okay?
Massimo, for the 3D version, does it automatically understand as well the corner free field columns?
Exactly. It does automatically the free field at the columns and at the vertical edges. It is all inside, okay? As you can see also here. The point is that you need a little bit more more combinations. But as I told you, now you can start playing with them. But by the next webinar, I will prepare an automation where you don't even need to model them. You can just pick the boundary faces and it will automatically create the extrusion and assign the proper boundary codes, okay? Yeah, I'm working on this. I didn't have time to finish it for this webinar, but it will be ready in the next couple of days. So for the next webinar, it will be even easier than this one, okay?
Okay.
Okay, so now we are running a little bit out of time. So, well, we don't have any light. Just a second, I need a light here. I prepared another example. Now we don't have time to go into the details of this one, but basically we have everything here. I prepared too much examples for today's webinar. Let me just show you the last one. Well, there are many others absorbing boundary examples. So there is the 2D, the same 2D with an imperfection. So there is a structure on the top. Then you have the 3D with distortion, which is actually these two here, the 3D, which is perfect one, and the 3D with a mesh distortion. And then finally, you have another example with two different layers. So where I modeled the bedrock and then another soil layer so that you can see how the wave passes through the layers. We have something else here in the chat. Where can we find that manual page? Is it already online? Yes and no, in the sense that I gave the code to the OpenSys maintainers. They included it on the online manual, but you have to compile it. Okay. So by tomorrow, I will also give a PDF of this one. Okay, together with this folder. So by tomorrow, you will find here in this folder also a PDF of this manual, because it will be compiled by the OpenSys maintainers, I think, during this month. Otherwise, you need to download the source code of the documentation and compile it. But I understand that not everyone is able to do it, so I will create a PDF of this one. Okay, so you have all the stuff here, and you have also a link to, let me go back here. You also have a link to an element that we use for the initial implementation, which is in 2D, and then we extended it in 3D. Okay, so you have a link here to this nice paper that gives all the theory. As you can see, the idea is the same. Okay, the problem is that it was 2D and we extended it to 3D. And it also gives you all the equations, okay, directly towards also to the matrix equation. So if you are interested in the theory, you can look at it. Okay, and then the last example I prepared, and unfortunately we are running out of time, which is a soil foundation structure interaction. I just want to show you the input and output, but actually I don't have to talk about it because actually it contains all the details I've explained today, all combined together. So if I go back in soil foundation structure interaction, what you can see here, okay, it is a soil here. Then you have the piles. Let me just isolate this one. You have a soil here with the piles, okay, with the excavation. So instead of having just one pile, I took the other model and I duplicated it, and I put a structure on top of it. And this structure also has a slab here. So you have both piles and the slab, and then a structure on top of it. And here you can see three different kinds of contact, which is the contact between the pile and the sides, which is basically this one. Select, okay, so same as before. Then you have the contact pile bottoms, select, same as before. And then you have the contact of the slab. This is really nice because it is using the from element option in such a way that you can combine a coarse mesh for the soil with a fine mesh for the slab. As you can see, the slab is meshed much finely. Okay, it's much finer, the slab mesh. And here, what I did is to perform all the. It's pretty similar in the structure to the example of the single pile. Okay, the only difference is that you have also a slab and a structure. So it is done in stages. So you have a first stage with the soil domain. You apply the gravity of the soil, you remove the holes, you apply the structure, you do the so you do the excavation analysis, then you add the structure, you do the settlement analysis, and then you apply a horizontal load and you do a pushover analysis. Okay, so you can go into it to understand how it works. I will just show you the output. And by the next webinar, what I want to do is to take this soil foundation structure interaction, which takes all the details I've explained about the contact element. I would like to extend this soil domain and apply free field condition and run a dynamic analysis on this. So this will be the topic of the next webinar, combining all these concepts with the absorbing boundary. Okay, so this is the kind of output that you obtain. Let me change a little bit the colors. As you can see, the difference between the meshes, but the contact can handle it pretty well. So now let me put a little bit more deformation and let me go back to the beginning. And this is what you can do here. Oh, and also let me hide part of the soil so that you can see what's going on inside. I want to remove this one. Yes. Okay, so in this first stage, you see the gravity analysis. without the holes. Okay, so here it is a full soil. Second stage, I remove the holes. Okay. Third stage, it goes back to the initial position and apply the extraction. Okay. And now here it starts doing the settlement analysis. Okay, now it will go down. Okay, and as you can see, the contact is working pretty well, even if you have a great difference between the slab and the soil. It is working pretty well. It does settlement analysis and then it performs the pushover analysis. Okay, let me go from the front view. Now I want to hide part of the structure so that we can see better the displacements here. Okay, and this is a shell, as you can see, so you can combine with this contact solids, beams, and shell all together. Okay, and in this analysis, it is extremely stable. 4 iterations for each step with the implex method and the Krylov Newton. Okay, so as you can see, this element is quite, as you can see here, you have a contact. Okay, contact here, and then you have a separation here. So yes, this element is it's just one single element, but we created a lot of automations that allows you to use it in different settings. So beam to solid, solid to solid, beam to shell, shell to solid. So it's quite flexible and really stable. Okay. So by the next webinar, what I will do is focus on this model only. Okay. I will answer some of your questions if you have questions about the contact. And then what we will do is to extend this soil domain, apply absorbing boundaries, and instead of doing a static analysis, we will perform a dynamic analysis of this one. Now here everything is elastic. I just wanted to focus on the contact. Okay, now here is everything elastic. But I prepared the model in such a way that you can change it if you want to experiment what happens with nonlinear material models. It will be released tomorrow. So by tomorrow, you will see on our website version 2.0.4. You will be able to download from Professor Tarke's website the new OpenSys version, and you will have the access to these files. Okay, so you will have everything by tomorrow. Okay, so let's say we have just a few minutes for questions because it took too much time. If you have any questions.
Hi, Massimo. Is it okay if I ask a question very quickly? Hello, can you hear me?
I can hear you.
Yeah. So you're talking about the next steps with the soil structure interaction model in 3D. You mentioned that you're going to apply the absorption boundary conditions and convert it to dynamic analysis. Is there a way to maybe also include several layers for the soil and give the layers non-linearities?
Yes, if you want to understand how it works with different layers, I already prepared a model for this, and you will be able to download it by tomorrow. Probably you missed it. Let me share the screen again. One of the files that I sent you, but I didn't have time to show you now, is this one. If you go back here, you go to absorbing, you have T05 absorbing 3D 2 layers.
Mm-hmm.
Here, basically, I was using the same file as before, so one single layer of soil, and then here I wanted to simulate. Actually, this is a benchmark, so I made a soil model here, which is linear, and then another linear material model here, which is 1,000 times stiffer than the other. It was just a benchmark to show that if I apply a velocity here that produces an acceleration of 1g, when it hits this surface, this interface, since this one is extremely stiffer than the other, here the acceleration becomes the double because I don't have any Rayleigh damping. And when it hits here, it gets double again because it is a free surface. Okay, but the concept is that you can see how easy it is, because basically you just need to create 2 absorbing material models. One that matches the material model for the first layer, and the other that matches the material model for the other layer. Okay, and you just need to assign them correctly. Okay, it is extremely easy actually.
All right, thanks a lot.
Welcome. Okay, so there is no other question. Thank you everyone, and see you soon on the next webinar. And yeah, by tomorrow, check the website, check the webinar webpage, because we will have all the things for downloading by tomorrow. Okay, so thank you everyone.
Thanks, Massimo. See you soon, hopefully in person.
Yeah.
Thank you, Massimo.
Hi, Wei.
Bye.
Welcome. Bye.
Thank you. Bye bye.
Thank you. Thank you.
Bye.
Bye.
Bye, everyone.